Our second speaker for the day is Antonia. She's going to be talking about emergence of R4 terms in M-theory. And yeah, please just take it away.
Yes, thanks for the introduction. And of course, thanks to all the organizers for the invitation. As you said, today we'll be talking to you about the emergence of R4 terms in M-theory, which was the topic of a paper that appeared recently on Archive, written with my supervisor, Ralph Blumenhagen, Niccolò Cribiori, and Alexander Kligovic. And it's also loosely related to a review we recently wrote, which is summarizing our current understanding of the emergence proposal. But before getting to the emergence proposal, which will be the main topic of today, let me try to keep this presentation self-contained and remind you how unusually things like in the Swampland program. And of course, the natural starting point is the Swampland Distance Conjecture, which tells us that at an infinite distance in moduli space, a tower of exponentially light states appears. And in fact, motivated by this proposal, we are usually looking at such corners of the moduli space where we might have a better understanding of the dual description of the theory that can be probed there. And thanks to the emergence string conjecture, we know that basically there are only two possible scenarios for what will happen. Either we're probing a decompactification limit or an emergence string limit. And while there have been many tests of these conjectures, many more conjectures related to them, the only other ingredient I will be needing today for getting to the emergence proposal is the species scale. Now, the notion of the species scale is interesting to us because in the presence of many light fields, the UV cutoff for an effective description of gravity can no longer be expected to be the d-dimensional Planck mass, as one would naively expect, but it is rather lowered by a factor related to the number of light species that appears in the theory. And recently, we have learned that there is a more precise way to think about this, which can also be useful away from these special corners of moduli space, which is to consider the higher derivative corrections to the effective description of gravity. And there we will find the species scale or other particular powers thereof, suppressing the higher curvature operators that appear in such corrections. Again, many interesting works have attempted to give us a better understanding of the species scale and to distinguish it from other relevant energy scales in the effective theory. However, we can already at this point recall the original formulation of the emergence proposal, which is telling us that the dynamics for all fields are emergent in the IR by integrating out towers of states down from an ultraviolet scale, which is below the Planck scale. And in fact, we are usually associating this energy scale to the species scale. Apart from this, one can usually extend this idea beyond the kinetic terms to also expect the emergence of other terms in the low energy effective action. There has been many interesting works leading to this proposal, as well as trying to better understand whether it can be realized or to some extent. But usually what we have in mind, because it's the most natural starting point, is an effective approximation of this proposal, which, to give you an example, would look like the following. If you consider that you have a light tower of states in your theory, their masses will be depending on the moduli fields of the theory in general. And then if you expand around these vacuum expectation values, this will induce correction terms in your theory, which at one loop can give rise to very simple Feynman diagrams, which can then help you identify the one loop correction to the field space metric. For example, in the very simple case of one modulus field, this is what this will look like. And while these results are interesting in their own, the question we would like to address today is where could the original strong version of the emergence proposal be naturally realized? And one of our initial attempts to tackle this issue was to consider the vector multiplet moduli space of type 2A string theory in 4 dimensions with n equals to 2 supersymmetry, where if you explore the moduli space keeping a fixed 4D dilaton, you only have 2 scenarios, as you would expect from the emergence string conjecture, either an emergence string limit or a decompactification limit, which can have also an M-theory uplift. And the interesting upshot of this initial attempt was that we found the exact emergence of physical terms, both for the prepotential and the free energy, at least in the simplified setup of the resolved conifold, only in the M-theory limit. In the emergent string limit, of course, one could get the full result also by applying familiar string-string dualities. But if one really wants to do an emergence-like calculation of integrating out the light states, it seems that the M-theory limit was the appropriate place to do so. And in fact, what we did was just apply an appropriate regularization technique to the Schrödinger integrals involving the full infinite towers of light states, which in this case were just bound states of D2 and D0 branes, revisiting the seminal work of Gopakumar and Vafa. The interesting new element was that this way we were also able to get the physical polynomial terms from such an integrating out prescription. So having such an example in mind, as well as the original formulation of the emergence proposal, one might think that we should better consider an M-theoretic refinement of this proposal. And what this claims is that in the M-theory limit, where the 11th direction will be large in units of the 11th dimensional Planck scale, denoted here by M star, with the Planck scale kept fixed, a perturbative quantum gravity theory arises whose low energy effective description is emerging by integrating out the full infinite towers of state with a mass scale parametrically not larger than the 11th dimensional Planck scale. And if you want to translate this into what kind of light state you should be considering, this narrows down the options to transverse M2 and M5 branes, possibly also carrying Kaluza-Klein momentum either along the M-theory circle or along any other compact direction potentially present. And of course, you can also translate this into type 2a variables by studying the limit carefully, and you will see that the light states from this perspective will consist of D0 branes and D2 or NS5 branes. And what one might think that it is very bold to make such a proposal just based on one example, but in fact, there seems to be deeper analogy to other approaches to M-theory, such as the BFSS matrix model, for example. Now, of course, I'm not saying that one can have a direct one-to-one correspondence, but what we would like today would be to take this refinement seriously and to confront it with a specific setup. So what we did more recently was to compactify M-theory on a k+1 dimensional torus, where in M-theory units, the 11th direction is large, so we'll be distinguishing it from the rest of the k compact directions. And as you could have guessed from the title, the quantity that we looked at was the R to the 4 coupling. Its coefficient is a 1/2 ppm saturated quantity and has already been determined by Greenwood, Perle, and Van Hove by considering the one loop for scattering, a one loop for graviton scattering amplitude in 11-dimensional supergravity. And already their ansatz is very close to an emergence calculation. What we have here is a Schrödinger-like integral where the light states that are being integrated out are just Kaluza-Klein modes, which are a subset of the light fields in the theory. And of course, if I want to be precise, such an expression always needs to be accompanied by a proper regularization method, since it can be UV divergent. And what they did was Poisson sum over all of the appearing integers and use T-duality for the remaining divergent term corresponding to all of these integers being equal to 0. But at this point, the natural question would be, okay, if the result is out there, and in fact it is calculated in a way very close to what we would think of as emergence, what more can we learn? If one goes through the details of that calculation, one can see that when they compactified M-theory in a circle, although they were able to get the tree-level term, the one-loop term, which is a constant in this case, was undetermined. It was formally divergent, and they just kept it as a constant that at this point was unknown. However, they applied their method again, they compactified down to 9 dimensions. They could again get the tree-level term and the Euclidean D0 instant and contributions encoded in this Bessel function. But again, the constant term is still naively divergent and unknown. Only through T-duality were they able to fix it to a quantity which in our units is 2 pi squared over 3, and then by the compactification determine it in 10 dimensions. So far, this is not too bad, only the constant term requires some special attention. However, if one continues following their approach, In 8 dimensions, the situation gets more complicated. Again, the tree-level term was easy to obtain, as well as the Euclidean D0 instanton contributions. But in order to get the full result, which could be matched also with the string theory calculation, one needed to add a series of instanton contributions by hand, as well as the appropriate logarithmic terms that would allow for the result to be modular invariant. And once again, we still have this naively divergent constant. And if you're more familiar with these results, you will recognize that there is a mathematical object that describes these amplitudes, which is called an Eisenstein series. And in fact, there have been many interesting generalizations of these calculations to lower dimensions, even a conjecture by Olbers and Paolin claiming that you always get the particular Eisenstein series in this limit, as well as more mathematical works trying to explore the behavior of these amplitudes. And it will be my goal today to persuade to you why the emergence proposal can actually shed some light on the ambiguities or perhaps the not so clear points of this very interesting calculation. But before I do this, one might still wonder, why not just go to our more familiar perturbative string theory limit and calculate the quantity from there, since that is also a possibility. And indeed, one can do a similar calculation in string theory and even express the result as an Eisenstein series, looking very familiar to what we had in the M-theory limit, where here by hatted summations, I'm implying that the term corresponding to all integers being 0 is excluded. And in fact, this expression is also a very easy way to remember that you're only including 1/2 BPS particles because we need the BPS conditions are imposed. And in this case, they have a very simple form of a linear Diophantine equation. Now, of course, since we have a well-defined perturbative limit in this case, it would be very surprising if the one-loop calculation could give us anything more than the one-loop result. But this is a chance for me to introduce to you the regularization procedure, which we will be following, which consists of introducing a UV regulator for the divergent integrals, applying minimal subtraction for the regulator-dependent divergences, and then zeta function regularization for the remaining terms. And observe that the final step would not be available to us if we were not integrating out the infinite towers of states that appear. If we were just cutting off the states at a particular level, as we would do in the FT approximation, then we would not be having infinite sums. And indeed, it seems that our regularization method works as expected, apart from the 10-dimensional case where we would just be getting a regulator divergency that we would be subtracting. In 9 dimensions, the method works fine. Going through the light stage, which are just winded strings and Kaluza-Klein modes, we can get the full one-loop result, including the one-loop constant term that was not determined in the M-theory calculation, but perhaps unsurprisingly, one cannot get much more. And in fact, this pattern is completely the same also in lower dimensions. One in principle can get the full one-loop result as long as one solves the BPS conditions, which is possible. But an interesting observation which comes out of this is that in all dimensions, we explicitly checked that this constant term always seems to be related to extended objects, in this case, winded strings. And perhaps this is also an explanation as to why we were not able to get it in 10 dimensions, where we cannot wrap the strings around anything. In any case, as we can see, in the emergent string limit, the one-loop calculation only gives us the one-loop result. So we are further motivated to focus again on the M-theory limit and take the M-theoretic refinement of the emergence proposal seriously. And what I mean by this is that we will extend the ansatz of Greenwood, Perl, and Van Hove so that it includes the full spectrum of light 1/2 BPS particle states. Now, in this case, again, the 11th direction is large, so we can only have Kaluza-Klein contributions depending on its radius. But here, I am collectively denoting any type of configuration allowed by the BPS conditions consisting of transverse M2 and M5 branes, or D2 or NS5 branes, in each of the cases that we will be considering. And in fact, I will also be using the same regularization technique, hoping that I have gained your trust in that it works. In 10 dimensions, it is perhaps unsurprising that when we apply our method, we get the same result as Greenwood, Perl, and Van Hove. We can get the tree-level result, but not the one-loop term. And in fact, this the situation is very similar also in 9 dimensions. Our method works fine. We don't need to make any further assumptions on the regulator apart from the fact that it's going to 0, and we can get everything but the constant term. The situation gets more interesting in 8 dimensions, which used to be the more problematic case of the Greenwood-Perle-Van Hove calculation. Now, we can also have light-wrapped M2 branes whose BPS conditions are known. Or equivalently, we can treat these contributions as contributions of bound states of D2 and D0 branes. At the end of the day, plugging this into our ansatz and performing the regularization, we see that we get precisely those terms that had to be added by hand in order to get the full result in the original calculation. In fact, we can apply the same method also for the Kaluza-Klein sector. We get the same tree-level and instanton contributions we would expect, and we are even able to directly obtain all of the logarithmic terms that would allow for the result to be modular invariant. But just to be honest about the details of this calculation, in order to obtain the precise logarithmic term, we also needed the input of modular invariance because, as you can see from this expression here, any additional scale introduced in the regulator could survive the zeta function regularization step and would affect our result. Now, this is not a mystery or a shortcoming of our calculation, but it is related to the fact that this Eisenstein series corresponding to this amplitude is actually not well defined at this point and needs to be regularized. This leads to this ambiguity, which can be solved by imposing modular invariance. And therefore, we can say that we have managed to obtain the complete result in 8 dimensions. Can we check this method further? Indeed, we can. What we did was we repeated this calculation also in the case of 7 dimensions, where we were able to get the full result. And in general, it seems that in all cases, 8, 7, and 6 dimensions, this pattern of constant terms coming from contributions of extended objects persists. And the situation was exactly the same in the emergent string case that we reviewed earlier. So we believe that this is why these constant terms are not available to us in 10 and 9 dimensions, because there is no light-wrapped M2 brane that we could have there. And in fact, one can even perform further consistency checks. One can predict what kind of instanton contributions we will be getting by the different kind of light states that we can include in the theory, such as D2 and S5 branes or Kaluza-Klein modes, and we see that we get all the expected contributions, including Euclidean D4 instantons, for example, even though D4 branes are not light objects to be considered. And what's more, our results are also consistent with more formal results related to the behavior of this amplitude. In fact, the initial conjecture of Olbers and Paolin was that one should integrate out all particle states to get this amplitude, which for us would only be relevant in the bulk of the moduli space, and we obtain the same result just by integrating out the light states in the strong coupling M-theory limit of the same theory. Only in this case, the result, as expected, preserves only the symmetries of the exceptional group in 1 dimension lower than the dimension of the compactification torus. And in fact, this equality here, even though it might be unexpected, it is related to the mathematical properties of these amplitudes. And practically speaking, it can be proved, and we have actually checked it in some examples, because there seem to be some very nice cancellations in this case of more states being integrated out. So having these very nice consistency checks in mind, let me already come to my conclusions. What we did was we tested the M-theoretic emergence proposal by extending the original ansatz of Greenwood-Perle and Van Hove so that it includes the full spectrum of light 1/2 ppm particle states. And in this case, this means that we are considering all states with a typical mass scale not larger than the 11th dimensional Planck scale, narrowing down the possibilities to transverse M2 and M5 branes and Kaluza-Klein contributions. And in order to actually calculate our results, we needed to impose a particular regularization technique, which was relying on the fact that we are really integrating out those full infinite towers of states. The upshots were that we could get the full results in dimensions 7 and 8, and make precise predictions on the instanton contributions in lower dimensions, as well as provide a physical interpretation for terms that seem to be ambiguous in earlier calculations. In fact, it is very satisfying that we could connect our swampland motivated reasoning to more formal works that were already existing in the literature. And in the future, what we would like to do would be to go beyond the umbrella of 1/2 ppm saturated quantities and also explore the connections between our approach to the emergence proposal and other approaches to it, such as the ones that have appeared recently, as well as try to understand what are the implications for other approaches to M-theory. So with this, I would like to stop here. Thank you for your attention, and I'm happy to take your questions.
Let's all thank Antonia for a great talk. And yeah, please, well, Alberto.
Hi. Thank you, Antonia. It was a brilliant talk. So I'm a little bit confused about what you say. So what is the motivation for choosing zeta function regularization? You're saying that you want to take the full tower into account, right?
Yes. Now, to be very clear, I do not have a microscopic reasoning for why it is justified to do this.
Yeah.
It seems to work. And so far, we have tested it multiple times. And we even initially, in other example, we even tried to actually stick to the effective theory approximation and see whether this can lead to sensible results. And this seemed to be more problematic. I would really like to understand what is the deeper nature of why we really need the infinite towers of state for this to make sense. Perhaps it is related to some more intricate property of M-theory, but it is not yet clear, unfortunately.
Yeah. I was asking because I remember, so when we were studying also these terms when going from 11 to 10 dimensions, and you can actually take into account the full tower within the EFT realm. Precisely what you do is, I mean, you compactify, you perform a Poisson resummation. As you were saying, this selects for you what is the universal piece, that the convergence piece associated to the full tower, and then a divergent term. For example, when going to 11, from 11 to 10D, as you were saying, this term actually diverges cubically. And you get the universal piece that is constant term is the free level piece in 10D type 2 string theory. And the other piece, if you actually fix your UV cutoff, your physical cutoff to be the species scale up to order 1 factors, you get also the constant term. Again, up to order 1 factors because you're not fixing it by definition. This is why I was asking, because I didn't, in some cases, it looks like if you actually do this procedure, you can actually select the convergent piece, which is kind of the thing that you were actually arguing for using zeta function regularization. But even using the species scale, sometimes you can even get at least up to 1 factors in this cubic divergent species, the exact answer. So I was a little bit confused by that.
Yes, no, indeed. If one really sticks to this effective field theory approach, usually the correct functional behavior can be obtained. But indeed, this is always up to certain numerical coefficients, whereas our goal was to try to get the full results, to not have to do any further fine-tuning, fixing of the regulator to a particular value, or any such bookkeeping, let's say.
Okay, thank you.
Thanks.
Hi, Antonia. Could I ask one question about the way you treat wrapped brain instantons? So when you have multiply wrapped brains, are you adding it with a factor of 1 or accounting for somehow for the degrees of freedom on the brains?
So you mean, for example, in results like this, right?
Yeah.
So what we were doing, we're just considering the particle excitations of the different excitations of the wrapped string. But I think this result is also compatible to the method of orbits and how one would obtain this result by looking at the multi-wrappings of instantons. So, if I understand your question.
Wait, so maybe I misunderstood. So are you like on a 5 torus or something, you would have like some wrapped fibrine, say, and if you had n wrapped fibrines on that torus, would you treat that as n light particles or a single light particle or?
Yes, yes, it seems so. Yes.
So there's a combinatorics in that treatment of the multiply wrapped brains, and you say it works in some straightforward way here. And presumably that's because of some kind of supersymmetry on the bound state structure of the branes?
We were only looking at 1/2 PPS conditions, so definitely we were heavily relying on the supersymmetry of the results.
Yeah,
Yes,
because I would think in general,
combinatorics are very nicely coming out so that one gets the full result. And in fact, this is also why, surprisingly, we can get the same results if we're integrating out any type of particle state and only the light particle states.
Mm. Yeah, I would be surprised if the same thing would work if you reduce supersymmetry. There has to be a point where it matters that there's stuff on the brain that has dynamics that will give different results in general.
No, definitely the amount of supersymmetry is very important for getting these results.
So could I also ask one really stupid question, just to because I'm just not following closely enough the emergence story. What is the precise statement of the emergence proposal in M-theory? What is it actually supposed to precisely state?
So originally, the emergence proposal was just a generic statement that the kinetic terms for all fields can be calculated by integrating out the towers of states down from some energy scale, which usually in Swampland we would associate to the species scale. Now, if you take this statement seriously, you would be expecting not just one loop contributions, which is what would naturally come out of a one loop calculation, at least if you're thinking of a perturbative theory, but also tree-level terms. And we were trying to understand in which cases could this actually be realized. And this is how we ended up in a particular corner of the moduli space, which is the M-theory limit, where we believe that indeed we can get all of the terms, or it seems to be that we can get also tree-level terms of the effective action by integrating out towers of light states. And we believe that, practically speaking, that states to be integrated out are those whose mass scale is not larger than the 11th dimensional Planck scale. Which, in a sense, if you actually do if you consider the limit carefully, would have the same scaling as the species scale. So in a way, the species scale for us is distinguishing between perturbative and non-perturbative degrees of freedom. And we believe that it seems to be that only in this particular case, integrating those perturbative degrees of freedom out can give the full result. So as I said, it's a refinement. We are not contradicting it. There's no disagreement. We just believe that perhaps the maximum strength of the emergence proposal can be found there if one is careful about how to approach it.
Mm. Okay, thank you.
Sorry, may I ask an additional question to Safdip's question?
Yeah.
So, but it's if you use the word precise, it seems to be crucial how exactly you cut off, right? Mm-hmm. I mean, there seems to be no a priori definition of that, because of course there are states which are also heavier. I mean, famously, string theory consists also of the excited states, of the excited string states. So where do you cut off? I mean, how can you make this precise in a universal way? I mean, without pointing to a particular calculation?
Well, as I said, in the terms that are being integrated out, we are not introducing a cutoff. We are actually integrating out those infinite excitations. Similar as for a string tower, you would have all of its excitations. The reason why we're excluding some states is if their typical mass scale is already beyond the cutoff of the effective description. So the minute the mass scale of a tower is below the species scale, we would be integrating out the infinite tower. But if the tower is heavy, we are not considering it.
But how do you distinguish towers? I mean, towers can also mix, right? I mean, in complicated situations, it's sometimes not clear.
Indeed, and so far, this is why most of our calculations were relying on particular Schwinger integrals in the strong coupling limit, which corresponds to M-theory, where it kind of makes sense that if you try to re-express this as a perturbative series, so if you want to look for tree-level, one loop, and so on terms, there is some mixing of terms.
I see. Okay.
In view of time, perhaps we can thank the speakers one last time. and I'll leave the Zoom open for further discussions. So yeah, thanks both of you for great talks.